Professor Haiyan. Professor Haiyan is extremely well known and I would say famous in China and abroad. He has been visited Germany and he speaks both languages very good, which is so difficult because they are so far, both of them, from Chinese language. So he is totally distinguished teacher. He is an academician of China, Chinese Academy of Sciences, and he received in America the Cody Medal for nonlinear dynamics. He has been president, actually, of two universities, major universities in China. He has been the president of the Nanjing University of Aeronautics and Astronautics. I think for about 10 years he was the president. And after that, he became the president of the Beijing Institute of Technology, also for, I think, 10 years. So, and he's also young. So, it's my great pleasure to introduce to Haiyan. I don't say what is his research field, he will tell us now. Thank you.
Thank you, Marco and Francisco, for your inviting me to this new island. Even though I've been to Italy many times, however, this is my first visit to Sardinia Island, and I enjoyed talking with you, in particular in this ancient building. So to show my worship to Italian civilization and culture, so today I dressed formally. Today I'm going to talk about, too close, the dynamics and topology optimization of soft machines, the study in these two universities that Marco just introduced to you. And to begin with, let me talk about the transition from conventional machines to soft machines. As you know, conventional machines are composed of rigid components such as gears, shafts, gears, and bearings to realize the desirable operation. However, sometimes those rigid components do not work very well. For example, in the case of a rigid manipulator of an industrial robot like this one, you need to well control the contact force if the manipulator is going to grasp a fragile workpiece. So in spite of the octopus, nowadays we are studying the soft gripper, soft manipulator, as well as soft machines, since more and more soft materials have been available. Today I'm going to talk about the study on the dynamic modeling and computation with collaboration of Professor Tian in BIT and dynamic topology optimization with Dr. Sun in NUAA. Now let me begin with the lecture of the basic introduction of the background. And from the school name, you can guess that my lab has been focusing on the aerospace structures, in particular with more and more soft materials and increasing commands for soft structures. So we are looking for the possibility to use and to apply these nonlinear dynamics to those soft machines. For example, the left video shows you the morphing process of an aircraft adaptive to different flight speed and different flight missions. And in the middle, this is the communication satellite in blue color. This satellite has not only, say, very flexible solar panels, but also a very large antenna. Let me talk about the middle picture. Shows you a communication satellite having a huge antenna for the telecommunication. And this antenna is so large that we cannot launch it directly. So we need to stow it into a small volume during the launch and then deploy it on orbit. To guarantee the successful deployment of the huge antenna, we did some experimental work at my lab. And here I can show you the deployment process, and you can see that the soft mesh is falling down due to the gravity. You may wonder, if the gravity vanishes on orbit, what will happen? Whether the soft mesh is falling down or goes up or goes to up, left or right. Nobody knows. Later on, I will address issue in the second part of my lecture. And the right picture shows you a light robot very recently made by my students. And this light robot is not only made of soft materials, but also subject to the topology optimization to greatly reduce the weight to less than, say, 15% compared with the conventional one. So I'm going to talk about the studies for those products, and then I need to solve some great challenges. Actually, according to the design of soft machines, we need to face with a great number of challenges. For example, the first one is a geometric nonlinearity due to the coupled overall motion and large deformation of a soft machine like the robot in the left video. In addition, we need to deal with the physical nonlinearity, mainly due to the nonlinear constitutive law of soft materials. For example, most polymers have different tension and compression modulus. And of course, some other nonlinear constitutive law that Professor Rubery just mentioned is more complicated. Well, the third challenge comes from the interface. And here, if you look at the middle picture and the right picture, you can see that the contact in the soft machines are not traditionally point-to-point contact, but the surface-to-surface contact between two soft bodies. This is a very essential issue. For example, if you are going to say no to the two ropes, just like the case of surgery operations, then you need to correctly predict the contact between the two ropes. Of course, in my case, I'm worried about whether we will have the mesh entanglement during the deployment of the antenna, in particular the soft mesh of reflector. So to deal with those great challenges, we need to have proper dynamic modeling and efficient and safety computation. And then based upon these techniques, it's possible for us to conduct the topology optimization, because these computations are very time-consuming and due to those nonlinearities. This is the major topic today. In my lecture, I'm mainly focused on the first challenge, what I mean that geometric nonlinearity. However, I will touch upon the second one and third one in some case studies. Okay, let's move to the second part of the lecture, talking about dynamic modeling and computation. Basically speaking, we have two kinds of methods to describe the overall motion and deformation of a flexible body. Depends on what kind of problem you are dealing with, depends on your previous experience. For example, if you are people in rigid body dynamics, maybe you are interested in the first type. However, the people in the field of continuum mechanics maybe are interested in the second one. Let me give you some basic introduction. First of all, if your body is subject to small deformation and your overall motion has a low speed of rotation, and this way In this case, you can establish a floating frame of reference, just like the, just like the, say, top right picture. And say, for example, you can describe the dynamic configuration or the movement of material point P positioned by vector R. And in this case, you can decompose the dynamic configuration into two parts. One is the overall motion, including the large rotation of your floating frame of reference, or called body frame. And the second part should be the small deformation of the body with respect to the motion of your body frame. Then this way, if the small deformation is small, it's natural for you to use the model reduction in structural dynamics. Then you can use, say, only the description of the overall motion of your body frame plus a few model coordinates. This way you can have an expression for your elastic force. However, the inertial force becomes very complicated due to, say, centrifugal force and Coriolis force, etc., because your body frame is subject to the large overall motion. This is the first approach. Of course, you can improve the approach, say, establish the body frame of your reference not only for the whole body, but for each cross-section of the body. Then introduce the theory of Lie group, for example, SE or 4, then you can have very accurate description of your geometry. We usually call it geometrically exact formulation. However, it's quite complicated. Now let me talk about the second approach, second description, which is familiar for the people in continuum mechanics, because here we do not need to distinguish the overall motion and large deformation. We can use the concept of dynamic mapping between the initial configuration and current configuration, just like Professor Rugri introduced to us. And of course, if you describe the motion of a material point P here, you can use the motion of neighboring nodes. Here, I need to emphasize that this motion is absolute motion because we do not introduce any floating frame of reference, but use a fixed frame only. So this gives the idea of the absolute nodal coordinates. Here, coordinates means motion. So I call it ANCF. Today, the major content of the lecture is based upon the ANCF, so I'm going to explain it in detail. Okay, to well understand the basic idea of ANCF, let's look at the simple case of two-dimensional slender beam. We are going to establish a nonlinear finite element method for the beam. So it's quite natural for us to look at the motion of point P, material point P, positioned by vector R. Recalling our previous experience in conventional beam element, we can certainly introduce, say, the cubic interpolation to describe motion of this point P. So in matrix form, we describe R is equal to matrix S multiplied by vector Q. And here, the entries in this matrix S are the same as those in conventional beam element. However, the coordinates in vector Q are quite different. It not only includes the conventional nodal coordinates here, for example, these two and these two. In addition, we have four nodal slopes to describe or to replace the deflection angles theta I and chi k in the two nodes of your beam element. Later on, I will explain the meaning of this replacement. Before going ahead, please keep in mind an important expression here. R equals to S multiplied by Q for later use. Okay, now let me talk about the replacement of slope with original flexion angle. Actually, if we look at the left end of the node, there are two slopes. We can put these two slopes here, these two terms, into a matrix. Then the second matrix tells you that it is nothing but the rotation matrix of a normal direction of the cross-section of your beam element. So very simple geometry. However, the conventional beam element, we use theta rather than sine theta. But you know, if theta is small enough, then sine theta is equal to theta, and cosine theta is equal to 1. So that's what this approximation means. This tells us that the ANCF can well describe the large deformation because we do not introduce any approximation in linear case. Okay, this is the first point. What about the overall motion of the beam element? That's quite easy for you to verify that. You can simply let your beam element undergo a large overall motion, including the translation and the rotation. Then it's easier for you to verify that the change of the nodal coordinates is nothing but the rigid motion of the beam element itself. So this way, I can say the ENCF beam element can well describe the coupled overall motion and large deformation. That's very important. The most important expression is here. R is equal S multiplied by Q. Then I will use it repeatedly. Following this idea, we have established, say, the three-dimensional beam elements, the thin shell element, and the solid elements, etc. For example, the 3D curved beam element we developed can be used to model not only, say, the slender beams, but also cables, mesh, etc. that are very important components in aerospace engineering. And the thin shell elements can well describe the thin plates, the shells, membranes, etc. The most complicated finite element we establish is solid element here with variable length. Why we need the length variable? Because in later on, when I talk about the topology optimization, and we don't know the shape of the structure and the component and even the software machine. So we require the element should be changeable. So in this case, each element has 8 nodes, and at each node there are 12 nodal coordinates, then plus 2 other coordinates to describe the variation of the length. Okay. Even though we have many kinds of elements, however, all of these elements yield this important relation. R is equal S multiplied Q. This is a very important expression. Then I will use it in next slide. Okay, after we have this description of movement, we can easily derive the kinetic energy, strain energy, and the virtual work of other sources, other forces. Then we substitute these 3 quantities into the Lagrange equation of the second kind. Then we have the dynamic equation of a single beam element, like this one. Here, I need to emphasize these 2 quantities. First, let's look at the matrix M. Because R is equal to S multiplied by Q, and S is the shape functions of the beam element, have nothing to do with time. So the time only appears in that Q. So we have R dot becomes Q dot, and finally you will see that in this quantity M is the inertial matrix has nothing to do with time. We have a constant mass matrix. This is the most important advantage of ANCF. However, when we get the benefit, we must pay. Pay for what? Pay for the complicated expression of the elastic forces. Here we have the strain energy for the electric forces, and Q is the stress tensor of the second Piola-Kirchhoff that Professor Rugri just mentioned, and E is the green strain tensor. So it's easier for you to imagine that the vector of electric forces should be very complicated because here everything are nonlinear. To deal with the problem, we need to use some basic knowledge of continuum mechanics. I had the same feeling with Professor Han-Chung Jiang that nowadays the young people do not love continuum mechanics anymore. So I often use this example to emphasize the importance of continuum mechanics. Anyway, the continuum mechanics I use today is much simpler compared with what Professor Rugri introduced to you. Here, I only focus on, say, the linear case of constitutive law, and Q, as mentioned, is the stress tensor, D is the elastic tensor of the fourth order, and E is the strain tensor, associated with the deformation gradient, F. I use the same symbol as Professor Rugri used. And in addition, we substitute the important expression R equals S multiplied by Q. Then we use an equivalent equation, Q bar multiplied by S bar. They have the same meaning but different expression for simple computation in later use. Anyway, as I mentioned that time quantity appears only in Q bar, and the matrix H has nothing to do with time. So substitute this expression into the strain energy, then we can derive our elastic force. During this process, maybe we need to do some tensor mathematics. However, it's not very difficult. The final result is important. After the factorization of all the quantities associated with time out of the integration, then it's easier for us to compute this integration before we start dynamic analysis. This gives you the opportunity to save a great deal of time, say 90% of time, and we only need to update the quantity related to Q bar. This is the importance of continuum mechanics. Okay, save the percentage of the computational time. Well, recording of the machine, besides the soft components, the machine may have different kinds of joints, such as the cylindrical joints and spherical joints described by algebraic equation. So after we sample all those components and joints together, we will have a set of differential algebraic equation like this one. The first line gives you the dynamic equation in the form of differential equation, and the second one gives you an algebraic equation describe the constraint of those joints. Anyway, we need to solve this set of equations, or called the DAE, numerically. Now there are several approaches available for solving this kind of DAE. Among them, I prefer to use the generalized alpha integrator. It's a kind of generalization of well-known numeric approach. It has an important feature of easier control of numerical distribution. Based upon the generalized alpha integration and Newton-Raphson iteration, we can transform the problem solving a set of DAE into a simpler problem solving a linear algebraic equation step by step in time domain. And usually we solve this equation for delta lambda first. That's a variation of your Lagrange multipliers, and then get delta Q. That's variation of your absolute nodal coordinates. Of course, you can speed up this process. For example, we can remove all the internal degrees of freedom of a single component by means of the subtraction method. In addition, you can also introduce parallel computation to speed up the process of solving linear algebra. The combination of these two skills can give you the opportunity to further reduce the computational time by 90%. Repeat. Remember, the first simplification gives you the opportunity, reduce it to only, say, 10%, and now 10%. So totally, we only use, say, 1% can complete a very complicated problem. Okay, now let me show you some macro-validation of the new finite element methods. We made some comparison of newly proposed beam elements with those, in particular, the solid elements in commercial software. The right figure shows you the comparison of the newly developed beam elements for the beams with eye cross-section and a rectangular cross-section and hollow rectangular section compared with the solid elements in ANSYS. And the left picture shows you the comparison between our result and the solid elements in Abacus. In Abacus, we use 1,600 solid elements to simulate the large formation of the beam. This approach works only for example, 3 or pi radius. It means half of rotation. However, the newly established beam elements plus the proposed approach of solving DAE can work for example, to 45 radius, much larger than the commercial software. So I can say this approach is superior than the solid elements in Abacus and save you a lot of computational time. Here, let me show you some, say, dynamic deformation. This is the twisting beam of eye section, rectangular section, and hollow rectangular section. And here is the spinning process of a rotating beam with a variable length. This is a quite important case for space industries. And here is a thin shell subject to buckling, and the thick shell subject to dynamic deformation, and the spinning memory deployed for the case of solar applications, solar energy power generations. Okay. Furthermore, let me show you some experimental validation. Here is the simple test rig developed at my lab. This is the flying net, very useful for capturing, say, disabled satellite or space debris. And the net is composed of a lot of strings and very, very light. And let me show you the videos. Unfortunately, the two videos are not synchronized, and in my own computer, the net is flying synchronously in numerical simulation and experimental studies. This is a relatively easy computation. You may wonder whether I properly describe the context between these strings. Yes, that's a very tough problem, not only for computation, but also for measurement. So let me show you a relatively simple test rig. And here the video shows you that the motor drives the top disk to spin, and the bottom disk connected with 3 strings rotates 2. And the motion of these 2 disks are not synchronized because of the inertia of the bottom disk. So you can see the 3 strings get in touch time to time and have the frictional context. How to deal with this problem in computation? We establish the beam model for those robes, and we can detect whether they get contact according to that distance. Say, determine the contact region after they get contact. As I mentioned before, the contact now is not the, say, point-to-point contact, but regional-to-regional contact between two soft bodies. So we need to accurately determine how large the contact region is, and then we can compute the contact forces. Say for the normal force, we use the Hose theory, and for the tangential force, we use the Lagrange model to well describe the static frictions, in particular to describe the well-known three-back effects. Okay, this figure shows you a comparison between the angular velocity of bottom disks, and you can see the computational result and experimental results get very good agreement to confirm the computation of contacts. Now let me show you a more difficult problem. Contacts. Here is the inflation of a pneumatic chamber. That's a very important actuators in soft machines. The chamber is made of very soft materials with Young's modular, only say 1 megapar, very soft. Initially, the chamber was bent into a circle, and then we let the airflow and the pressure 500 par to inflate it. Here, I give you the deployment process. You can see the very complete contacts of the chamber itself. To look at the case in detail, I'll give you 3 specific moments, and you can see the contacts really happen, not only point to point, but regional to region. Okay, when we confirmed everything of approach, then we deal with a real engineering problem, talking about the communication satellite in the very beginning. The top figure shows you the satellite in blue color. It has the 2 solar panels in gray color and a white microwave feed source in white color, supported by a truss, deployable truss in black color. The most important thing is that the satellite has a huge antenna, much larger than the satellite itself. As I mentioned, we have to study this antenna before and during launch, and then let deployed in orbit. So we use the beam elements, plate elements of NCF to model this real engineering problem. And the bottom picture shows you the deployment sequence step by step. If you look at the video, it can show you the process vividly. And here I do not include the deployment of the soft mesh because it's too complicated. Let me demonstrate it later on. The problems, as I mentioned before, is that we need to testify the correctness of the computation by means of the ground test. And in ground test, we cannot remove the gravity effects totally. We tried to eliminate the gravitational effects applied on the truss by means of a cable pulley system like this one. We compensate the gravity by means of some lumped mass. However, it's not possible for us to do so to remove the gravitational effect on the soft machine. So during the deployment, the soft machine must fall down due to the gravity. So our task is to accurately compute the falling down process of the mesh. If this is okay, then we can remove the gravity in computer to predict the right deployment process in time on orbit. So let me show you the comparison between the numerical simulation and the ground test. Unfortunately, the 2 videos are not synchronized due to, say, the project. In my own laptop computer, you can make very good comparison of these two processes, predict in computation and measured in experiment. Anyway, to see the comparison result, I give you, say, the results at 4 specific moments, and you can see, if you compare, say, the bottom figure and the top figure, you can see actually the real get good agreement. And finally, I give you a figure, shows you the comparison of deployed angle, measured and computed. They really get agreement, except for the case at the final stage, there is some fluctuation because of the friction in the joints. We cannot control those frictions very well in experiment. Okay, this is the end of the second part, and now let me talk about the third part, that is the dynamic topology optimization. Topology optimization means how to get the best distribution of a given material, for example, for a single structure like a cantilever beam, say this one. Of course, we do not have any suspended cables. I use a simplified case here. We need to, say, allocate our material in this gray domain we call design domain. To simplify the problem, we mesh the domain into a lot of rectangular cells, and we can determine how much materials we need to put into the specific cells. For example, if a cell E is fully occupied by the material, then I define a parameter PE be positive 1. If your cell has nothing, what I mean that it's void without any material, then I put PE be 0. So here PE is the design variable, or physically a relative density of your material, of your structure. Of course, during the topology optimization, you must have some cells with lower density, not black and not white, but gray, say, in those cases. So finally, we have the results like this. The top one looks like the chipboard. Why? An important reason that we do not have enough fine mesh. If you have fine mesh, then the things can be improved. However, it's not easy for us to do so because finally we try to get the middle one. However, the number of design variables are just the number of the cells, and it determines the computation cost. So it's not possible for us to use humorous number of cells to get the result. Then how to do? You may quite straight ask me, is it possible for us to have the final result like this one? It has only 8 bars or 8 components. The answer is yes and no. Let me say no first, because you don't know the geometric shape before your optimization. You don't know how many components, you don't know where it is and what are the shapes. So why I can say yes? Because this result reminds of the possibility that we can replace those rectangular cells by means of a few components, but with a changeable place, changeable orientation, changeable size, and changeable shapes. If this is true, we can certainly greatly reduce the number of design variables. This gives us the concept of moving morpho component, or called M&MoCS for short. Now, in this figure, we simply replace the original rectangular cells by using much fewer number of components. For example, if we look at the component omega I, actually we need only, say, the position of the geometric center, the orientation theta I, and the length AI, and height BI. See, we only use 5 parameters can determine the right position, right angle, right figure shape, and right size. So meanwhile, we can introduce a function related to this omega I to determine whether we distribute, whether we allocate mass. So the union of all those functions give us the possibility to describe the topology information of the structure you are going to optimize. And the final result should be this one. And during this process, maybe we can remove some components. Here, the components have a changeable size, changeable place, and changeable state. If you imagine it's kind of the procedure of playing toy Lego made in Denmark, and then the Lego should be moving and morphing and finally get the final optimization. Okay, based upon these knowledge about the topology optimization, that is for the static problem, let's talk about the dynamic problem. During the dynamic topology optimization, I need to address two important issues. First is that we have transformed the topology optimization to the parametric optimization by means of the vector of a lot of design variables. In addition, in each update procedure, we need to solve this equation. This is the original DAE. For each time step, for each update of your parameters. This is certainly very time consuming compared with the static problem. One skill to reduce the computational time is to keep the computation of this ODE for each step of your updated design parameters. However, if you use any method of gradients, for example, the standard method of moving asymptotes, you need to calculate the Jacobian of the system dynamics with respect to the change of your design variables. In this step, I simply replace this dynamic equation into an equivalent static one to save the time of computing those Jacobian, or called dynamic sensitivities. This gives you a great deal opportunity to save computational time. The second issue compared with the static problem is that your design domain may not be fixed. It may be changeable with time. If this is the case, we can introduce the idea of virtual domain. And in the virtual domain that your structure has not deployed to that case, you can simply let all the forces in the virtual domain vanishes or be zero. This also simplifies your approach. Okay, this way we can do some real optimization. Here I give you two examples. The first example is the right picture in my very beginning introduction. It's a very light soft robotics made by some students in Nanjing last semester. And the robot has one body and 4 legs, and each leg has 3 links connected by 2 carbon joints. The major task of the optimization is to reduce the weight of both body and all these legs. So we set a volume ratio to say 0.15. That is, we are going to remove 85% of the mass out of the conceptual design. The left 2 pictures shows you the optimization process with the iteration again and again, and finally we get the satisfied shape of the body and satisfied the shape of the legs. And here are some videos to show you the flexibility and capability of the small robot. It's very light. Okay, this looks like exercise for some toy machines. The second example is more realistic in engineering. Here I'm going to talk about a deployable satellite system, and the top figure shows you the major configuration. In the center of the system, we have a major satellite. Then we have 3 small sub-satellites connected by deployable and inflatable booms in yellow color. See, this is the case of the boom deployed. Here, the video shows you the deployment process due to the inflation of the beams. What is the use of this satellite system? Let us look at the video. And here, in the center satellite, there is a microwave feed source. Send out the electronic waves to your target. And then 3 receivers in 3 sub-satellites receive the reflected microwaves. And this way, the satellite becomes a radar with a very long baseline, which can be used to detect a small target in sky, other planets, for example, in very high resolution. For this purpose, we must reduce the vibrations of all these 4 satellites as much as possible. This is very important work for dynamic analysis and topology optimization. In the very beginning of the study, we look at the case of a small model. The boom deployed only, say, 3 meters long rather than the real case, and we use Yoshimura tube to construct the booms, and we did some experimental studies to testify the vibration and deformation in different inflation rate. And here you can see the video, and if inflation at 25 liter per meter, then it moves forward, but upward a little bit. And then if we let inflation much faster, then the deformation becomes very large and together with some strong vibration. So is it possible for us to design the booms based on the concept of topology optimization? Let's look at the case. And the right picture shows you the optimization process. Here I set the volume ratio to 50.5. That is, we need to remove 50% of materials. And you can see the blue curves goes down continuously. This is the amplitude of vibration. So implies that with iteration of your optimization, the vibration becomes smaller and smaller. And the left 3 pictures show you the optimized shape of this boom. And here, the blue color means the thick wall, and the yellow color means thin wall. So you can see the blue color goes to the clamped end and horizontal plane, and the yellow color goes to the free end and the vertical plane. You can see the optimization result more clearly if you cut the booms along its axle. Then this way you can see these 3 figures quite clear to see in what place the wall is thick and in other place the wall is thin, and that's what we need. Now let me show you the vibrations before and after the optimization in black color and in green color respectively. The comparison tells you that the optimization gets very good result to reduce both in-play vibration and out-of-play vibration. We get very satisfied result. However, the story is not over. When we submit the results to engineers told us that in order to have different images of the space missions, they ask us to look at the case when the 3 receivers move slowly along the boom, when the boom is fully deployed. So we simplify the receiver as a lumped mass like this and made a numerical simulation and experimental study to testify the variation. Here, for example, the bottom figure gives you a comparison of the first bending frequency compared with different mass locations. Okay, further studies showed us that the high order frequency behave quite complicated. For example, with increase of the distance between the lumped mass and the central satellite, the second frequency of bending and the first frequency of torsion will change their order through this view here. So the engineers worried about that if there is possible internal resonance happens. So they asked us to do the optimization again. And here we have the final result. And you can see that we do have a gap with those bending frequencies and torsional frequencies. And this way, the engineers feel satisfied and ask us to complete the study. Okay, that's the story. Now, before conclude my presentation, I'm going to summarize in 3 sentences. The first is that the approach we proposed enables one to model and compute the complicated nonlinear dynamics of soft machine in a very efficient way and greatly reduce the experimental study. The second, if we combine this approach with the topology optimization, then gives you a very powerful tool to design soft machines in practice. Furthermore, nowadays we are looking for the possibilities for some even challenging space problems, such as the morphable and reconfigurable space structures. And if the space structure is too large, for example, over 100 meters, we cannot deploy it further. We must assemble the modularized space structures step by step by means of the space robots. So these problems give us a lot of new opportunities and also great challenges. So we are studying the advanced integration of nonlinear mechanics and dynamic control, as well as artificial intelligence embedded into those approaches to solve those tough problems in future. Thank you so much for your attention.